All right, so we're in section 2.3 now. We're going to be dealing with introductory derivative rules and marginal analysis. So in the first couple of sections of this chapter, 2.1 and 2.2, we were developing the idea of the derivative. We started with the concept of instantaneous rate of change and slope of tangent lines to functions. And from that, we came up with this idea of the derivative, which we defined as the limit of a difference quotient. We have now gone through a bunch of examples finding derivatives of functions, and it's a somewhat tedious process. Evaluating that limit oftentimes will have several steps, and it just doesn't feel practical to have to do that every single time we need to compute a derivative. So fortunately, we have a whole bunch of shortcuts for dealing with derivatives, so that we never really need to deal with that limit definition again. It's important that you know that limit definition because it's embedded in there is kind of the concept of rates of change and things like that. But now that we are past that phase of learning the concept, we can start plugging away at working out derivatives in a much more efficient manner. So what I have here are a table of several different derivative rules. Now, if this were a course in, a full course, I should say, in calculus, so like a calculus 1 course, or sometimes we call it engineering calculus, we would spread these rules out a whole lot more. We wouldn't just give them all to you right away. And the reason for that is because we prove all of them in a full calculus course. This being business calculus, we tend to not get into the really rigorous stuff, and we don't really prove all of these results. So we're going to just give them to you. I will talk through the logic behind some of them, because it is important for you to kind of have a sense of why these things work. But beyond that, we're going to just kind of take for granted that they work. So in this table, we have rules for taking the derivatives of several different classes or types of functions. So if you want to take the derivative of a constant function, let's say k is just some constant, then the derivative of that will always be 0. We'll talk about why that makes sense in a minute down here. Power functions, which are functions of the form x to some power, and that power does not have to be an integer. It can be any real number. So we can think of n as being a rational exponent if we want to. We can think of n as being an irrational number if we want to. It doesn't really matter. This rule always works. And this one we're going to be using a whole lot. We call this the power rule. And if you are doing this, you're taking the derivative of x to the n, then that exponent of n will come out into the front of that x. So you notice there's an n here, and then we subtract 1 from that exponent. So the n comes down, subtract 1 from the exponent. Now we have n times x to the power of n minus 1. There's a special case of that one that is worth singling out, and that's the derivative of just the function y equals x. Its derivative is just 1. And the reason why is because, you'll see this in parentheses here, that function can be thought of as x to the power of 1. So if we apply the power rule to it, that 1 comes down. 1 times x is still just x, so the 1 doesn't even need to really be written there. But then we subtract 1 from the exponent, and that's 1 minus 1, which is 0. Well, x to the power of 0 is just 1, because anything except for 0 itself to the power of 0 is 1. So that is going to just reduce that down to the constant 1. That's an important special case, so it's mentioned there. Exponential functions, where it's a function of the form b to the power of x. When we take the derivative of those, we get b to the power of x times the natural log of that b, whatever that base was. A couple of things worth pointing out about this. First of all, it's not uncommon for first-time calculus students to confuse power functions with exponential functions, but they are two very, very different things, even if they look very similar. So power functions put the variable in the base, and the exponent is a constant. Whereas exponential functions, the base is a constant, and the exponent is a variable. So people make this mistake the first time they take calculus. They try to take derivatives of exponential functions and they treat it like it's a power function, and they bring the x down and they subtract 1 from the x like we do up here. That does not work for exponential functions. It's a different rule entirely. So you have to make note of that. Also, the other thing I wanted to point out, this natural log of b, since b is a constant, then the natural log of b would also be some constant. So really what happens when you take the derivative of an exponential function is you get some constant multiple of itself. Another way of saying that is that the derivative of an exponential function is proportional to itself. That is a unique property that exponential functions have. And in fact, depending on your approach, you can even define exponentials that way. You can define them as the class of functions whose derivatives are proportional to themselves. Not that important for us, but it is worth pointing out. There is an interesting special case of this. That's if you let e be your base. The derivative of e to the x is just e to the x. And we can see why that's the case here. If I take that e and use it as my b here and here, the natural log of e, which is what would be in here, is just 1. So that just leaves me with the e to the x that would have been there in the first place. So the special thing about this is that e to the x is not just proportional to its derivative, it's equal to its derivative. It's exactly equal to its derivative, which is kind of a cool property. All right, moving down to the next one, logarithms. Kind of similar to exponential functions in the sense that the natural log of your base is making an appearance, except it's not in the same place that it appears. If we want to take the derivative of log base b of x, that comes out to 1 over x times the natural log of b. Remember, again, natural log of b would be a constant. So it's 1 over a specific constant times x. Worth looking at a special case of this also, which is when b is set equal to the constant e, making this the natural log. The derivative of the natural log function is literally just 1 over x. And it's the same reasoning as the exponential function. If I'm plugging an e in for the base b here, I have the natural log of e, which is 1, times x, which is just x. So that, again, that special case makes a lot of appearances throughout calculus. Finally, these last two rules are a little bit different from the previous ones, because here for the sum and difference rule and the constant multiple rule, we're not talking about derivatives of specific types of functions. All of these are specific types: constant functions, power functions, exponentials, logarithms. But here we're talking about general functions, just any f and g for which a derivative exists in the first place. If you want to take a derivative of a function that comes from adding two functions or subtracting two functions, then we can just take the sum of those derivatives, if that was a plus there, or the difference of those derivatives, if it's a minus there. So another way of saying this is that the derivative of a sum of functions is the sum of the derivatives of those functions. Constant multiples also have a nice convenient rule. If I have some function f of x and then I multiply it by a constant k, that gives me another function. If I take the derivative of that, what I get would be the same as if I had just pulled this k out completely, taken the derivative of f of x, and then multiplied that result to k. So this constant multiple rule says that we can basically take a constant times a function, and then when we take its derivative, the constant can be pulled out of that derivative like this. Okay, so we'll use all of these. A lot of them we'll use in combination with one another. But before we do that, I want to talk through a little bit of the reasoning behind some of these rules. So that's this paragraph right here. Starting with the very first rule, if you think about the constant function, the derivative of k, where k is just any constant, the graph of a constant function always looks like a horizontal line. So, did I put a picture of this anywhere? I don't think I did. No. So if you want to imagine the graph of a constant function, y equals k, those always look like these horizontal lines. So that's f of x equals k. But horizontal lines, remember, derivatives represent slopes of tangent lines at particular points. No matter what point I choose on here, I can just see visually the tangent line is going to be the same as this line itself. It's going to be horizontal. And if a tangent line is horizontal, then its slope is 0. And that's exactly what we're saying here. Regardless of where I chose that point, the derivative or the slope of the tangent line to that function will always be 0 because it's always horizontal. The power rule, we have seen this occur over and over again when we did derivatives in the previous section of functions, because we dealt with a lot of power functions. We never specifically drew attention to the fact that this pattern was happening every time. But if you go back and watch through those videos or look through those lecture notes, you'll see this happening every time we want to take the derivative of a power function. So here is an example that kind of confirms that the power rule is working for a specific function, x to the 4th power. That's a power function. It's x to a constant exponent. And if I were to take the derivative of this and just pretended for a second that I didn't know the power rule, I would have to go back to my limit definition. And that would be this limit right here. Limit as h goes to 0 of x plus h to the 4th minus x to the 4th all over h. This x plus h to the 4th expands out, and it gets a lot of terms when it does, but you get this, x to the 4th plus 4x cubed times h plus blah, 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 blah. And then I have that minus x to the 4th still there. Notice that this x to the 4th and this minus x to the 4th would then cancel out. And all of the terms that remain at that point have at least one factor of h in them. I can then cancel this h with one of each of these h's. This h is the only one in this term, so I get 4x cubed as a result. All of the other terms still have at least one h left over after canceling. So that's important because, as we saw, once you apply that limit, you can use the direct substitution property, making all of these terms go to 0. Now I'm left with 4x cubed. So this was using the limit definition of a derivative, but the result was exactly what was predicted by the power rule. Remember, the power rule says that if you take the derivative of a power function, I can take the 4 in the exponent in this example, bring it out front, and then subtract 1 from that exponent. So that's what looks like happened here. A 4 came down. I took the 4 that was in the exponent before, but I subtracted 1 from it and got a 3, 4x cubed. Okay, so, and then finally, we have one more on the next page where we prove this very last result, the constant multiple rule. It's the only one that I want to do an actual, like, formal proof of, just because it's so straightforward. So if I wanted to take the derivative of a constant k times a function f of x, we can go to the limit definition for that. The limit of as h approaches 0, using this function, I would have k times f of x plus h minus k times f of x all over h. Notice in my numerator here that k shows up in both terms. I can factor that k out of the numerator, which I'm putting it down here to show that. And then I can use the constant multiple rule that we have for limits, which says that constants times a function, you can pull that constant out of the limit. So the k comes out here. But then if you look at what's left, limit as h approaches 0 of this difference quotient, that is the very definition of f prime of x. That's your derivative. So I have k times f prime of x, and that is the constant multiple rule. Again, if we wanted to be really rigorous with this, we could prove all those different derivative rules that we just talked about using a similar argument where we kind of break things down from the definition of a derivative, but that's not what this class is. So what we want to do is practice using those rules. So here we're going to find the derivative of 5 different functions by using some combination of the rules on that previous page. The first one is the easiest one. So I have y equals x to the 10th. I want y prime, the derivative, and it's a power function, so I just need to apply the power rule. The 10 comes down, and then I subtract 1 from my exponent, 10x to the 9th. That's the whole thing. That's it. Super straightforward. This next one looks a little bit more complicated. So It's actually not, but we're going to break this down into more steps than we are going to be doing in the future. So if I want to find f prime of x, then I'm taking the derivative of a sum and a difference of 3 functions. So I can think of this as 9x to the 5th, that's one function, minus 7x squared, that's another function, plus 19, that's a third function, constant function. Our sum and difference rule says that we can evaluate the derivative of a function like this by taking the sum or difference, depending on whether we have a plus or a minus here, of the derivatives of these functions. So I have to take the derivative of 9x to the 5th minus the derivative of 7x squared. I didn't leave much space here, so that's okay. Plus the derivative of just 19. Okay? This, I can go another step further and notice that some of these terms have constants times a power function in them. And we have that constant multiple rule that says that constants can come out of derivatives. So this is equal to 9 times the derivative of x to the 5th. I don't actually need parentheses there, so I'm going to leave them off. Minus, I can bring that 7 out, 7 times the derivative of x squared. And then here, this is not a constant multiple, it's just a constant. The derivative of a constant function we already know is equal to 0. So that would be like plus 0 right there, and I'm not even going to bother writing that. Okay, next step, each of these derivatives that are left are the derivatives of power functions, so I can use my power rule. I have x to the 5th, so the 5 comes down, and then I subtract 1 from my exponent, 9 times 5x to the 4th, minus 7, this guy, the 2 comes down, 2x to the first power, because I subtract 1 from 2. But if you have something to the first power, you don't really need to write the 1 there. It's the same thing as 2x. And then finally, I can simplify. So multiplying the 9 and the 5 here, for example, 45x to the 4th minus 7 times 2 is 14x. This would be my final answer. Okay? And unfortunately, I didn't do a very good job with my spacing here, but that's all right. We'll do that to kind of separate it. You will never again see me spend this much time on taking the derivative of a polynomial, because in practice, nobody actually goes through and writes all of these steps. I did it here because I wanted to show you how I was using each of those rules. But what I would have done instead, once I have, gotten some practice with these rules, is I would just go to this first term and think, okay, power rule. Bring the 5 down. There's already a 9 there, so the 5 multiplies to that 9. I get a 45. Subtract 1 from the 5 there, and I get 4. That's my power rule and constant multiple rule in one step. Okay? Take the 5, multiply it to the 9, subtract 1 from the exponent. Notice I just get that first term. Same thing here. Take the 2, bring it down and multiply it to the negative 7. Now I have negative 14. Subtract 1 from the exponent, and I have an x. And then finally, this constant term, I know its derivative is 0. It goes away. In future examples with polynomials, I will go from here directly to here because you don't need all of this extra work, okay? This problem, I have to kind of work around here. Y equals the square root of x. So if you go back to your, your table of rules, in fact, we'll just go over there, you're going to see that there's no radicals showing up anywhere in this rule, in this table. And that's the reason for that is because radicals can be thought of as power functions. So they're already accounted for there. The way we do this is we take that y equals the square root of x, but we rewrite it with a rational exponent. Y equals x to the 1/2 power. Now I can apply my power rule to this, and it's really straightforward. The 1/2 comes down, and I subtract 1 from my exponent. 1/2 minus 1 is negative 1/2. Now I could leave it in this form, or since I started with a radical, it seems appropriate that I end with a function that has a radical in it. So another way of writing this same function is 1/2, that's the 1/2 right there. The fact that this is a negative exponent means I would move it into the denominator, x to the 1/2 down there, or square root of x. These are the same function, just using different notation to represent it. So I'm going to write it that way. Okay? All right, since I already did this once, I'm going to go like this. Just to keep things separate. Next one, g of x equals e to the x over 5. One thing that we do as we move on in mathematics is we learn that there really isn't a unique operation called division. Now, that's not entirely true. I mean, division is an actual thing, but I guess what I mean by that is that anytime you're dividing by something, you can reinterpret that as multiplication. And we do it this way. G of x is equal to 1/5 times e to the x. This is just 1/5 times e to the x. And the reason I'm doing that is because we have a rule in our derivatives that tell us how to deal with constant multiples of functions. I have an exponential function, e to the x, and a constant times that function. It didn't say anything in that table about a function divided by a constant. But by reinterpreting it this way, we can use that constant multiple rule. So I'm going to do more steps than I normally would here. We want to take the derivative of 1/5 e to the x. Constant multiple rule says that the constant that's being multiplied to the function can be brought out of the derivative. And then I'm just left with the derivative of e to the x there. E to the x was that special case that's equal to its own derivative. So that's just 1/5 e to the x. And it turns out that this function is also equal to its derivative. In fact, there was nothing special about the 1/5 here. You can see that regardless of what constant I put here, this would have come out to its own derivative. So that leads us to kind of a general result. The derivative of any function of the form some constant times e to the x will be its own derivative. One more to go. Okay, we want to take the derivative of y equals the natural log of x squared. Now, as of right now, we don't have a rule for dealing with this because we have a rule for dealing with the natural log of x. We found that was another special case on our table. Its derivative is just 1/x. But this isn't the natural log of x. This is a composite function. I'm taking a function of another function. Later on in this chapter, towards the end of this chapter, we'll talk about something called the chain rule, which tells you how to take derivatives of composite functions. But we haven't gotten there yet. So why is this problem showing up here? Well, you can dodge the need for the chain rule by using a logarithm property here. Remember, any logarithm of something to the power of something, you can take that exponent out of the logarithm and put it out front. So this is really the same thing as 2 times the natural log of x. Now I have a constant multiple of a function. Over here, I wrote out all of these steps. I'm not going to do that anymore. Y prime is equal to 2 times the derivative of the natural log of x, 1/x. A simpler way of writing that would just be 2/x. Okay, so as you can see, we just worked through 5 separate derivatives in a tiny fraction of the time it would have taken us to do all of these with the limit definition. And in fact, we would have gone much faster if I wasn't being careful to show all of these steps in some of these problems, which we're not going to continue doing. You just kind of need to see that one time, and then we can work through these at a much faster pace. All right, let's do some more in the next video.